Alright, we're doing problem 72 from chapter 5 of Organic Chemistry. This is going to be a question about, involve a lot of concepts. I have not attempted this yet, so we're going to go through my thought process and see if we're able to actually get this done or not. So, first part of the problem, draw both cis and trans parts of this molecule in their more stable chair conformations. So to do this, I think it's just best to draw a cyclohexane as such, and then draw the chair conformation, and draw it both ways, and then identify which one's more stable. So this is our cyclohexane. We're going to be looking at 1,4-dimethyl 1,4-dimethyl cyclohexane. Okay, so already what I can tell here is if we were to draw the chair conformation of this, these um, methane groups have to be equatorial. If they're axial, it's going to have 1,3-diaxial strain. And 1,3-diaxial strain, diaxial strain is going to have a type of steric repulsion between the methane groups and like the other hydrogen stationed on the molecule, which is going to repel each other and be less stable. So now I think we should draw. I think we should make. Let's just make this the cis version. I'll make this a cis version. Both of them are hashes. So now if you were to draw the chair conformation of this, start off with this, boom, 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 boom. This was actually a terrible chair. Start like this, as such. This could be a hydrogen right here. This could be axial up, equatorial down. This is going to be a methane group. Axial up, axial down, axial up, axial down. Equatorial down, equatorial up, equatorial down, equatorial up. Since this is supposed to be so this right here is supposed to be cis, right? Because they're both uh, observing this cyclohexane from the top position, top down. These methane groups are under the cyclohexane ring. They're under it. If they were facing up, you would see the methane group pop up at you. But that's not what we're observing because these are dash marks down. So, regardless of that, a methane group has to be placed right here. Now, this will result in 1,3-dioxyl strain because this is an axial position, and this is going to have some effect on this hydrogen atom right here and this hydrogen atom right here. Axial up, axial down. You know, it's going to affect this and affect that as well. But, I mean, let's draw, if we were to draw the chair flip of this, what would that look like? Well, this is equatorial down, it's now going to be axial down, and this is axial down, it's now going to be equatorial down. the down and up positions stay as down and up positions, but the axial turns to equatorial and the equatorial turns to axial. So instead of axial down, it'll be equatorial up, equatorial down, it'll be axial down. Now that won't change the molecule in terms of its stability, because you're still going to have at least one methane group having 1,3-diaxial strain on the molecule. So I think our other bet here is to draw the trans version of this. And then we just have to make one of these such. If we were to draw this molecule, I think the way I draw it now, it will in fact have to be flipped, but we'll deal with that. That's good practice. So this is axial up. Here's our methane. Okay. Sorry, I think I'm drawing. Sorry, these are not methanes. See, I just caught that now. These are just methyl groups. I don't know why I was saying methane. Yeah, that wouldn't have worked. Sorry about that. Well, this is a problem to see. No rehearsal, no nothing, just straight into it. We make mistakes. Okay. So, methyl. Axial up because it's pointing upward. The hydrogen's pointing downward. Axial up, axial down, equatorial up, axial down, axial up, equatorial down, up, down, up, axial down, equatorial up, equatorial down, axial up, axial up, axial down, and then equatorial up. Okay. Axial up. This has to be facing downward. This is carbon 1, carbon 2, carbon 3, carbon 4. Methyl, so 1, 2, 3, 4. So methyl group right here, it's down. It's actually going to be axial down. So yeah, both of these are having axial strain, 1,3-diaxial strain. So we have to actually flip this. And if we are to draw this flipped, I'm going to have to draw something like this. Now this moves clockwise. So now the 1's here, 2's here, 3's here, 4's here, 5's here, 6 is here. Label these. Okay. So this methyl group axial up. Axial up. It's going to be equatorial up. Axial down. And then 4 axial down. It's going to be axial down. It will be equatorial down. So that's methyl. Hydrogen. Now this is the most stable conformation. Most stable. No 1,3-diaxial interactions. Okay. I think we should also note same stability. as flip. Now let's think about the flip. So the flip version, this is equatorial down right here. It's going to be axial down. Instead of axial down here, it's going to be equatorial down. So that's going to be the same here, and that's going to be the same here. So it's the same, basically the same. Who would have thought, guys? How many stereoisomers are there of cis 1,4-dimethyl cyclohexane? And how many of the trans 1,4-dimethyl cyclohexane? Well, I hate to break it to you, but if we were to look at the cis molecule right here, of the cis 1,4-dimethyl cyclohexane, it has, so there's a hydrogen attached to that, then there's a carbon, there's another carbon, and then there's a third carbon. One of those carbons is that methyl group, and those other two carbons are literally just these that go and just connect all the way over here. They're the exact same thing. Its two substituents meet up at the exact same carbon down here. So this thing has a line of symmetry right down the middle. So the cis version is achiral. This is an achiral molecule for the cis version. So there are 0 for the cis. Now for the trans, let me think. I want to say the same argument can be made, but I'm not too sure. I'm saying the same argument can be made because there you still can draw a line of symmetry down the middle. But I think it's good. Now I think it's a good time to perhaps draw RNS configurations. So, in fact, let's try. Maybe we can, even though we established that this is achiral, I think we should maybe. I don't even want to. No, there's no need. You can't draw no stereoisomers on this because it is achiral. It has a chiral carbon right here. Um, for this, whether there's no stereo center because it's an achiral molecule, right? Okay, now this one right here. Okay, is there a stereo center? That's what I'm thinking right now. Is there a stereo center? There's not. There's no stereo center on either one of these compounds. There's no stereo center because there's a line of symmetry down the middle. Whether or not cis or trans, both of these are achiral. So no. To answer part B, no. There's also 0 of these. Because you might be thinking, what if I turn this wedge into a hash and I turn this hash into a wedge? Sure, you can do that and you might think you have a new molecule, but you don't. You don't. You just don't. Right? You can flip this over a mirror. You can draw a mirror, draw it again, draw this wedge right here with a hash, and then draw this hash right here with a wedge. And you might be thinking, oh, this is a new molecule. No, it's not. It's the same molecule rotated 180 degrees. If that's the case, that's not a new molecule. That's it's the exact same thing. Okay. What are the stereochemical relationships among the various stereoisomers of 1,4-dimethyl cyclohexane? So, it's asking the relationship between the cis and the trans version, and cis and trans isomers are always diastereomers. That's what it wants you to know. So this is a diastereomer. Boom. And then that's the problem.